A computer is often described as an intelligent machine that thinks, understands, and makes decisions on its own. In reality, a computer has no understanding, awareness, or consciousness at all. It does not know what it is doing, why it is doing it, or what its actions mean. A computer is simply an extremely fast and precise machine designed to process information according to fixed rules. At its most basic level, every computer works with very simple states. Everything inside a computer is reduced to two possibilities: signal or no signal. These two states are commonly represented as ones and zeros. From these simple building blocks, all complex operations are created. A computer does not see text, images, or videos the way humans do. It only processes numbers that represent those things. If you like similar educational content, please like, subscribe, and share the video with your friends. When you type a letter on a keyboard, the computer does not recognize a symbol or a word. It receives a numeric code. When you watch a video, the computer does not see motion or color, but millions of values describing brightness and color of individual points on the screen. When you listen to music, the computer does not hear sound, but processes numerical descriptions of sound waves. Meaning exists only in the human mind, not inside the machine. The true strength of a computer is speed, not intelligence. It can perform billions of extremely simple operations every second. Tasks that would take a human years of repetitive work can be completed by a computer in moments. However, the computer never understands the task. It only follows instructions exactly as they are given. If the instructions are flawed, the result will be flawed as well. Historically, computers were created as calculation machines. Their original purpose was to perform mathematical operations and repetitive computations. Over time, engineers realized that the same mechanism could be used to process text, images, sound, and communication. Computers became universal not because they became smarter, but because almost everything can be represented as data. For a computer to function at all, it must be organized. There must be a place where data is stored, a place where it is processed, and a way for different parts to communicate. Without this structure, a computer would be nothing more than a collection of disconnected electronic components. To truly understand how a computer works, the next step is to look at its fundamental building blocks and how they cooperate to form a working system. For a computer to do anything useful, it must be built from several key components, each with a clearly defined role. A computer is not a single intelligent unit, but a system made of specialized parts that constantly exchange information. Only when these parts work together does the computer become functional. The most important component is the processor, also called the central processing unit. The processor is where actual computation happens. It does not permanently store programs or data. Instead, it continuously fetches instructions, interprets them, and executes them one by one. Each instruction is extremely simple, such as adding two values, comparing numbers, or moving data from one location to another. The power of the processor comes from its ability to execute these tiny steps at incredible speed. To work efficiently, the processor needs working memory, known as random access memory. This memory acts as a temporary workspace where programs and data currently in use are stored. When you open an application, it is loaded from long-term storage into memory so the processor can access it quickly. This memory is very fast, but it is temporary. When the computer is turned off, everything stored in this memory disappears. Long-term data storage is handled by storage devices. These hold the operating system, applications, documents, photos, and videos even when the computer is powered off. Storage is slower than working memory, but it is persistent. The computer constantly moves data between storage and memory depending on what is needed at any given moment. All these components are connected by the motherboard, which acts as the central communication platform. The motherboard contains the pathways that allow data and signals to travel between the processor, memory, storage, and other components. It also distributes electrical power and keeps everything synchronized so operations happen in the correct order. In addition to these core parts, computers often include specialized components such as graphics processors for image rendering and input devices that allow users to interact with the system. However, none of these components can function independently. A processor without memory has nothing to process. Memory without a processor cannot do anything, and without the motherboard, communication would be impossible. A computer is therefore a carefully coordinated system. Once powered, it still cannot act on its own. It must first be brought to life through a precise startup sequence. That leads directly to the next question. What actually happens when you press the power button? When you press the power button, the computer is not immediately ready to work. No programs are running, the operating system is not active, and the processor has no real tasks yet. However, within a few seconds, a carefully ordered sequence of events takes place that transforms inactive hardware into a functioning system. The first step is the delivery of electrical power. The power supply begins providing stable voltage to the motherboard and all connected components. This stability is critical because electronic circuits require precise electrical conditions to function correctly. If power is unstable, the computer will fail to start or shut itself down to prevent damage. Once power is stable, the processor enters its initial startup state. At this moment, it does not load software from the disk or memory as it normally would. Instead, the processor knows exactly where to look for its very first instructions. These instructions are stored in a small memory chip on the motherboard that contains the computer's startup code. This startup code performs basic checks to ensure that essential components are present and functioning. It verifies that working memory is available, that the processor itself is responding, and that basic input and output systems can operate. If a critical component fails this check, the startup process stops to prevent the system from running in an unstable condition. After these checks are completed successfully, the computer searches for the operating system. It looks through connected storage devices to find a valid system installation. When it finds one, it loads the most important parts of the operating system into working memory and transfers control from the startup code to the operating system itself. From this point on, the operating system takes over. It activates full processor functionality, manages memory usage, initializes storage access, configures hardware components, and prepares the environment needed to run applications. Although this stage appears very fast to the user, it involves a large number of coordinated operations that must happen in the correct order. Only after this process finishes is the computer truly ready for use. What users perceive as a turned-on computer is actually the final result of a complex startup sequence that began the moment power was applied. At this stage, the computer is active but still passive in behavior. It waits for instructions from the user or from running programs. To understand how it can process those instructions so quickly, we need to look deeper into how the processor actually works internally. The processor is often described as the brain of the computer, but this comparison can be misleading. A processor does not think, reason, or understand. Its job is to execute extremely simple instructions, one after another, at very high speed. Every program, no matter how complex, is broken down into a massive sequence of tiny operations that the processor can perform. At the core of processor operation is a repeating cycle. First, the processor fetches an instruction from working memory. Next, it decodes that instruction to determine what action needs to be taken. Finally, it executes the instruction, which may involve performing a calculation, comparing values, or moving data between locations. Once this cycle is complete, the processor immediately moves on to the next instruction. This process repeats continuously billions of times every second. The speed of this cycle is controlled by the processor's internal clock. Each tick of this clock represents a tiny slice of time during which part of the instruction cycle advances. A faster clock allows more steps to be completed per second, but speed alone is not enough to achieve high performance. Modern processors are designed to handle multiple instructions at different stages of execution at the same time. To accomplish this, processors use a layered execution approach, While one instruction is being executed, another may be decoded, and a third may already be fetched from memory. This overlapping process keeps the processor busy and minimizes wasted time. As a result, even complex software can run smoothly despite being composed of countless simple steps. Processors also rely on extremely fast internal memory to store data that is likely to be needed immediately. Accessing this memory is far quicker than retrieving data from working memory, which helps reduce delays. By predicting which data will be used next, the processor can maintain high efficiency and avoid waiting for slower parts of the system. It is important to understand that the processor never sees a program as a whole. It always operates on small fragments of instructions, responding only to the current step. Decisions in a program are made by evaluating simple conditions and branching to different instruction sequences based on the result. All higher-level logic emerges from these basic operations. This design makes computers incredibly versatile. Any task that can be broken down into logical steps can be processed by a computer. However, the results of this processing are still just data. To become useful to humans, this data must be transformed into images, sounds, and interactive responses. That transformation is the next critical part of how computers work. Inside a computer, everything exists only as numbers and logical states. Yet for the user, the computer appears as images on a screen, sound from speakers, and instant reactions to input. This transformation from raw data into something humans can perceive is a continuous process that happens many times every second. Visual output begins with the graphics system. A computer does not understand an image as a picture. It treats the screen as a large grid made up of tiny points, where each point has a numerical value describing its color and brightness. These values are stored in memory and processed by the graphics hardware. The graphics system rapidly converts these numbers into electrical signals that control the display. Because this happens very quickly and repeatedly, the human eye perceives a stable and smooth image rather than a constantly changing set of data. Sound works in a similar way. Audio inside a computer is represented as numerical descriptions of sound waves over time. The sound system converts these numbers into electrical signals that drive speakers or headphones, causing air to vibrate in patterns that our ears recognize as speech, music, or noise. The computer itself does not hear or understand sound. It simply processes mathematical representations of waveforms with great precision. Equally important is the flow of information in the opposite direction, from the user to the computer. When a key is pressed on a keyboard, a mouse is moved, or a touchscreen is tapped, the computer does not receive a letter, a gesture, or an intention. It detects a change in an electrical signal. That signal is translated into a numeric code, which the operating system routes to the appropriate program. From there, the processor decides how the program should respond. This exchange of input and output happens constantly. The computer listens for input, processes data, updates internal states, and generates new output. This cycle repeats many times per second, creating the illusion of real-time interaction. The speed of this loop is why modern computers feel responsive and smooth, even when performing complex tasks. None of this would be possible without software. Hardware provides the ability to move and process data, but software defines what the data means and how it should be handled. The operating system coordinates all hardware components, ensures programs can run safely, and manages communication between devices. Applications then build on this foundation to perform specific tasks. At this point, the computer can accept commands, process information, and present results. However, despite its impressive abilities, it still has clear limits. Understanding those limits explains why computers behave the way they do and why they will never truly think like humans. Computers often appear intelligent because they can solve complex problems, analyze massive amounts of data, and react faster than any human ever could. They can recognize faces, translate languages, generate text, and even beat world champions in difficult games. Despite all of this, a computer does not understand anything it does. Every action is the result of strict rules, calculations, and predefined structures, not awareness or comprehension. A computer has no goals of its own. It does not know why it is performing a task, nor does it care about the outcome. It follows instructions exactly as they are given. If those instructions are incomplete, incorrect, or poorly designed, the computer will still execute them without questioning their meaning or consequences. There is no intuition, common sense, or internal understanding guiding its behavior. Even systems described as artificial intelligence do not think in the human sense. They are mathematical models trained on large amounts of data to detect patterns and probabilities. When such a system produces an answer, it is not reasoning or reflecting. It is selecting the most likely output based on statistical relationships learned from data. If the situation falls outside those learned patterns, the system can fail in unexpected ways. Computers are also constrained by physical limits. They depend on electrical power, signal speed, and heat dissipation. Every operation consumes energy, and every component has limits on how fast and how efficiently it can operate. No matter how advanced technology becomes, computers will always be bound by the laws of physics. The true strength of computers lies in reliability and scale. They can repeat the same operation millions of times without fatigue, process enormous data sets with precision, and perform tasks that would be impossible for humans to handle manually. They excel at structure, repetition, and speed. What they lack is understanding, meaning, and intention. A computer is therefore best understood as a powerful extension of human capability. It amplifies what people design, program, and instruct it to do. Humans define the goals, interpret the results, and decide how the output should be used. Without human intent, a computer is simply an inactive system of electronic components. When we say that a computer works, what we really mean is that it efficiently transforms electrical signals into logical operations, stores the results, and presents them in a form humans can understand. This process can be extraordinarily complex and fast, but it is not thinking. It is execution. Understanding this distinction removes much of the mystery surrounding computers. They are among the most powerful tools ever created, but they remain tools. Their capabilities reflect human knowledge and creativity, not independent intelligence.